and we're going to start talking about continuous probability. Well, I mean, we've been talking about these normal bell curves, and they were examples of continuous probability, but now we're going to officially enter the realm of continuous probability. How do we work with probabilities when the possible outcomes have no gaps between them? Bear in mind that before, with discrete probability, when we looked at the result of a die, 1, 2, 3, 4, 5, 6, these were nicely spaced out possible values for x, the result of one die. The possible values of x were nice and discrete. You could easily list them, organize them nicely. However, they did not fall on a continuum. In continuous probability, we allow for values like 1.1 or 1.01. Now in lesson 19, we're going to start with continuous uniform distributions, which are the most basic category of continuous distributions. And we're going to discuss the relationship between probability and area. Basically, in pictures like these, there's a direct relationship between areas and probabilities. In fact, areas are probabilities. And we can talk about that even in the context of discrete probability. While we're at it, let's review these examples from discrete probability. So in part A, we'll discuss probability histograms and ideas of area. Before, we could use probability histograms like these to describe discrete probability distributions, such as the one for the result of one die rule. And this is an example of a discrete uniform distribution because the probability for each possible face was the same. It was 1/6. So for example, what's the probability of getting a 3 on one die? Well, it corresponds to the area of the corresponding bar. And how do we get the area of this corresponding bar? Well, area is given by, you know the formula, area of a rectangle is given by base times height. Here, the base, or the width here, is 1 unit. We're going to assume that each of these bars has width 1 unit. The height is the probability, 1/6. And therefore, the area of this bar in here, the area of the bar inside here, is going to be 1 times 1/6, or 1/6. That's the probability of getting a 3. The probability of getting a 3 on one die is 1/6, which is the area of this corresponding bar. Now, these are probabilities for individual outcomes. The probability of getting a 1 is 1/6. The probability of getting a 2 is 1/6. The probability of getting a 3, as we saw, was 1/6, and so forth. But in general, we can also talk about the probabilities of events corresponding to areas. So again, if each bar has a width of 1 unit, then the probability of an event equals the total area of all the bars corresponding to that event. So for example, what's the probability of getting an odd number? Well, what are the odd numbers? The odd numbers on a die are 1, 3, and 5. The corresponding probabilities or areas are 1/6, 1/6, and 1/6. Again, discrete uniform, these probabilities are equal. The probability of getting an odd number is the sum of these probabilities. 1/6 plus 1/6 plus 1/6, that's 3/6 or 1/2, which is the total area of all the shaded bars in this figure. The probability of getting an odd number was P of 1 plus P of 3 plus P of 5, 3/6 or 1/2. Okay. Now, we're going to go from bars with flat tops to more general curves. We talked about normal bell curves before, but now we're going to talk about flat tops. Okay, flat tops, just guys like these. These are continuous uniform distributions. But still, I'll refer back to these bell curves for reference. In part B, we'll talk about probability density functions. When working with a continuous distribution, we use a probability density curve, such as this bell curve over here, or this flat top guy over here, instead of a histogram. The curve here is called a probability density function, or it represents a probability density function. So here are properties of a probability density curve and its density function. The area between a probability density curve and the x-axis is 1. So the area between this bell curve and the x-axis is 1. The area between the flat top and the x-axis will be 1. All right. Again, the area here will correspond to total probability, which is 1. If the probability density function is f, in general, we can call a function f, then f of x is greater than or equal to 0, meaning it's non-negative for all real values of x. This means that the density curve never falls below the x-axis. So for example, this bell curve here would never fall below the x-axis. That never happens. That never ever happens. The bell curve always has to stay above the x-axis. In principle, you can bounce off the x-axis, but you never fall below the x-axis. Okay, so our most basic continuous distribution is the continuous distribution of this type, the continuous uniform 0-1 distribution, the continuous uniform distribution on this interval of values. And in fact, random number generators generally have this type of distribution. So you often find this in software packages or on calculators. Random number generators often give values for x, where x has as its distribution a continuous uniform distribution on this interval from 0 to 1. This distribution is perhaps the most basic continuous distribution, even more so than the bell curves. The value of x in this case can be any real number between 0 and 1. And in fact, on Excel, there is actually a function, the rand function, which spits out generates or iterates from this distribution. So rand here, this is the description on Excel. Rand returns an evenly distributed random real number greater than or equal to 0 and less than 1, basically between 0 and 1. A new random real number is returned every time the worksheet is calculated. Now, these random numbers are really pseudo-random numbers. They come from an algorithm. In this case, the Mersenne twistor algorithm. I can't really describe that to you, but this is a link to a Wikipedia article on it. But for all practical purposes, we can think of them as random because the algorithm is so unpredictable in its nature. So in Microsoft Excel, the command is, well, equals RAND, and then you put a pair of parentheses. And here is a random number between 0 and 1 from that continuous distribution. We could have a list of 10 of them. So here we have a list of 10 random numbers between 0 and 1. Again, many scientific calculators will spit out these kinds of values from this distribution, a continuous uniform 0-1 distribution. Now, the density curve is flat like this. The probability density function f is given by the rule f of x equals 1, where x is a real number between 0 and 1. So here, x can take on values between 0 and 1. The height is 1. The area of this square, well, it's a 1 by 1 square. The area under this flat top curve is 1, and that represents total probability, 1. The area of the total rectangle is 1. For any continuous distribution, the probability of any particular value is 0. So for example, let's say that 0.3 is over here. So 0.3 is over here. Okay. But if you look at the corresponding area, really it's just a line segment. And what's the area of a line segment? The area of a line segment is just 0. So technically, the probability that x takes on exactly the value of 0.3 is 0, which might seem a bit contradictory because we're claiming that 0.3 is a possible value of x. It's a number between 0 and 1. It's a number that could be spit out by this Excel spreadsheet. So there's a bit of a paradox here, and it really stems from calculus. There are infinitely many possible values between 0 and 1, and they're splitting up this total probability of 1 among these infinitely many values. So that's really a calculus idea. Even though the probability of each individual value is 0, we're still saying that values such as 0.3 are possible. And I realize this may seem contradictory from when we talked about discrete probabilities. Again, it's a calculus idea. In fact, when you look back at the description on Excel, so technically the rand function could in principle spit out a 0, but it cannot spit out a 1. But we don't have to worry about that because technically the probability of getting exactly a 0 or exactly a 1 is 0 anyway. So here, when I was defining this distribution, I said that x could be any real number between 0 and 1 inclusive. Really, it didn't matter whether we had the bars here or not, because the probability of getting exactly a 0 is 0, and the probability of getting exactly a 1 is 0. So we don't even have to worry about the bars here, whether they're there or not. So again, for any continuous distribution, the probability of any particular value is 0. For example, the probability of a 0.3 is 0. That's the area of this line segment. In fact, it's the area of any line segment, including the ones at 0 and 1. And yet, we can say that these various values are possible. But how do we assign positive probabilities then? How do we assign positive probabilities? It is only possible to assign a positive probability to an interval of values for x. So for example, well, the probability of getting something between 0 and 1 is 1. We can assign positive probabilities to areas of, say, rectangles or bars like these. But these bars, maybe rectangles or squares, will correspond to intervals of values. Here, the area of this bar is the probability of getting between a 0.3 and whatever this is, maybe a 0.5. For a continuous uniform distribution on an interval, the probability mass is spread out evenly on that interval. So pieces on the interval that have equal width will correspond to equal probabilities. So for example, let's say that the interval here is the same width as the interval here, from here to here. Then for a continuous uniform distribution, the area of this bar here will equal the area of this bar here, and the corresponding probabilities are equal. And that's true for continuous uniform distributions if you're talking about intervals that are between 0 and 1. We're going to talk about particular calculations and computations with this distribution in the next lesson.